Hello student, today we will discuss a new chapter of physics, that is magnetic effect of electric current. That means if current flowing through a conductor, then how magnetic field develop around the conductor. In this case we will discuss that is called known as magnetic effect of electric current. We know, suppose we have a bar magnet, and if we take a magnetic needle near the bar magnet, then the magnetic needle deflect itself. Why? Due to the magnetic effect or due to the magnetic lines of force of the bar magnet. Clear? So in this case, we will discuss what is magnetic effect of electric current. Clear? Suppose we have a conductor and current flowing through the conductor I in this direction. Clear? And suppose we have a charge particle Q which is at rest, then this charge particle will not experience any force. That means no effect or no experience any force. Clear? Next thing, same conductor and current flowing through the conductor I, same situation. If there is a charge Q and same charge this Q, and this charge which moving with velocity V, that means this charge particle which moving with V velocity near a current carrying Y. Clear? Then this charge particle experience a force and it deflect this direction. This is the direction of charge particle due to some velocity V. But initial situation, when charge particle is at rest, it will experience no force or it does not experience any force. But when this charge particle, when this same charge moving with velocity V, then it deflect its path. That means it will experience any force. Moving charge which experience any force. And this experiment first done by Oersted or Oersted's experiment. That means due to the motion of a charge particle near a current carrying Y, then the charge particle experience one type of force which is not electrostatic force, because suppose this is the direction of electric field, and if we place a charge particle Q which is at rest inside electric field, then this charge particle experience a force, and that force is known as F equal to Q into E. Clear? If this charge particle placed near a current carrying Y and a current flowing through the Y I, then this charge particle no experience any force. But here, if this charge particle moving with some velocity V, then it will experience a force. And in this case, if charge particle rests in electric field, then it will experience a force. Similarly, if a charge particle moving with some velocity towards the electric field, then it will experience a force and it deviates from its original path. Clear? So this type of force and which experience a force, this force is not electrical force, or this force is not electrostatic force. This is another one type of force, and that force is known as magnetic force, or that effect which is experienced by moving charge, that effect is known as magnetic effect, which is not electrostatic effect. Clear? So in this way we can say, according to Oersted, if there is a current carrying wire and current flowing through the wire I, then a moving charge experience a force due to magnetic effect. That means magnetic effect develop around the wire, and that magnetic effect due to the current carrying wire. Clear? So from this experiment we conclude that if there is a current flowing through the conductor I and charge it at rest, then it will experience any force. That means the force experience, it does not experience any force. It does not experience any force. And same thing, if there is a current carrying wire and current flowing through the wire, right, and there is a charge particle which is moving with velocity v, then it will experience a force. That means force acting on the charge particle is not zero, and due to this force it deviates from its path. So if there is a moving charge, then this charge will experience a force due to magnetic effect. If this charge is at rest position, then this charge particle will not experience any force according to Oersted. Next thing, suppose we have a current carrying wire and current flowing through the wire I. If we take a magnetic needle inside the current carrying wire, this is the magnetic needle inside a current carrying wire. Suppose this is the initial case and there is no current initially. This is a conductor, there is no current initially, and this is the direction of north pole and this is south pole of the magnetic needle. Clear? If current flowing through the wire I, that means if we connect this terminal positive potential and this terminal negative potential, then current starting from positive terminal to negative terminal, due to the flow of current or due to the flow of charge inside the conductor, then current flowing through this direction, and we found that the magnetic needle which is near the current carrying wire, then it deflects in this direction. Why? Due to magnetic effect. From this experiment we also conclude that when current carrying wire, when current flowing through a wire, then around the conductor, around the current carrying wire, that develop a magnetic field due to which this magnetic needle deflect. Similarly, this is the current carrying wire and we can change the polarity. This is negative and we change it to positive, and this is negative, and this is the direction of current. So in this case, if we take a magnetic needle, this is the initial situation when there is no current. After flowing through the current I through the wire, then the magnetic needle deflect in this way. Clear? So this is the direction of magnetic needle, deflect in this way when current flowing through this terminal, and it is fast situation when current flowing through positive to negative terminal, the magnetic needle in this way, then this is the magnetic needle in this way. So from this experiment we conclude that if there is a current carrying wire and magnetic field develop around the wire, suppose this is a current carrying wire, this is the wire and this is the flow of current. Clear? If this is the direction of flow of current, then if we take a magnetic needle here, then this magnetic needle deflect, then the magnetic needle deflect itself due to magnetic effect, and that magnetic field around the current carrying wire in this way. This is the direction of magnetic field, or we can say this is the direction of magnetic field inside a current carrying wire. Clear? This is the direction of magnetic field. If this is the current carrying wire, current flowing through this direction, then magnetic field develop around the wire in concentric circle like this. Clear? this is the magnetic lines of force for a current carrying wire. This is the direction, this is the shape of magnetic lines of force for a current carrying wire. In this way, the magnetic field develop around the wire and the center of all the concentric circular ring are equal. That means, and the magnetic lines of force always perpendicular. This is the magnetic lines of force, and this magnetic lines of force which is always perpendicular to the flow of current or direction of the current. Clear? This is all about Ørsted experiment, and we can write. Suppose we have there is a circuit connect through a battery. This is positive terminal, negative terminal, and one key K, and there is another one instrument rheostat. This is connecting Y. Clear? Suppose this point A and this point B. After closing the key K, for a constant current, suppose we have a magnetic needle below this wire, and this is magnetic needle, and this is south, and this is north pole of the magnetic needle. Clear? When the circuit is open, there is no deflection for the magnetic needle, and this is south, this is north. Clear? When this key is closed, when circuit is closed, then current flowing through the circuit is I, and this is the direction of flow of current. Because when current flowing through the wire from A to B, then according to Ørsted, magnetic field develop around the wire, due to which this magnetic needle deflect and this north pole deflect this direction. This is the final situation. This is the final situation of the magnetic needle. That means after current flowing from A to B, the magnetic needle deflect, which conclude that there develop a magnetic field around the wire, which show deflection of the magnetic needle. Clear? This is all about Ørsted experiment. So, from this experiment or from Ørsted experiment, we conclude that current carrying wire current carrying conductor produce magnetic field around it. Clear? This current carrying conductor produce magnetic field around it in this way. This is magnetic lines of force. Next point, if current flowing through the conductor I increase, then magnetic field strength around the conductor increase. That means if current increase, then magnetic field strength also increase and vice versa. If current decrease, then magnetic field strength also decrease. Next thing, this magnetic lines of force which always perpendicular, this magnetic lines of force always perpendicular to the flow of current. That means if this is the direction of current and this is magnetic field lines, and this magnetic field lines and direction of current That means magnetic field lines, perpendicular to the flow of current or conductor. Clear? Next point. Next point. There are number of magnetic field lines which consisting circular loop with there are number of magnetic field lines which consisting circular loop which consisting concentric circular loop which consisting concentric with the conductor. That means this is current carrying wire I and this is the direction of magnetic field lines and the angle between this magnetic field line and current carrying wire is 90 degree. There is number of magnetic lines of force. This is the magnetic lines of force. It's the diagram of magnetic lines of force in this way. Clear? This is the direction of current and this is the direction of magnetic field line. Direction of magnetic field line and this distance, radius are equal and then also you can draw. This is another circle which is concentric. That means the center which passing through current carrying wire. Clear? This is all about our state experiment. So, if this is the direction of current and this is the direction of flow of current, then this is the direction or this is the magnetic lines of force around this current carrying conductor, and in this way the magnetic field develop around the conductor and this magnetic lines of force which is always perpendicular to flow of current. Clear? So next we will come snow rule. Snow rule means here we have to determine the deflection of deflection of north pole of the or determination of deflection of north pole of the magnetic needle. So for the direction of deflection of north pole, if we place a magnetic needle inside a current carrying wire. Clear? And this rule, first rule is known as snow rule. Snow rule. This is the direction of the east, west north south direction. Clear? Suppose we have a magnetic needle and this is north pole and this is south pole. Clear? If there is no current carrying wire. Now, if we take a current carrying wire over the magnetic needle, that means this is the current carrying wire. And this is the current carrying wire. Connect through a battery. This is negative terminal and this is positive terminal. When key is closed, then current flowing through this direction. That means this is south, this is north, south to north direction. This is the direction of flow of current. Clear? According to Snow rule, this is the initial situation of a magnetic needle and this indicates north pole and this indicates south pole. Clear? This is initial situation when there is no current flowing through the wire. After circuit is closed, the current flowing through the wire from south to north. Then the magnetic needle deflects itself towards west. That means this is initial situation of the magnetic needle. When current flowing through the wire from south to north, then magnetic needle deflects itself towards west. And this rule is known as Snow rule. That means when current flowing through the wire from south to north direction, then magnetic needle deflects itself towards west due to magnetic effect. And this is the direction or determination of north pole towards west direction when current flowing through the wire, that is south to north. Clear? And this rule is known as Snow rule. Why Snow rule? When current flowing from south to north over west. The meaning of Snow rule. That means SNOW. When current flowing from south to north over west direction, then the magnetic needle deflects towards west, and this rule is known as Snow rule. Clear? So you have to remember this shortcut method. That means when current flowing from south to north over a magnetic needle, then the magnetic needle deflects itself towards west. Then the magnetic needle deflects itself towards west. So this is Snow rule, and you have to remember this shortcut method. Next we will go Ampere's swing rule. So what is Ampere's swing rule? So now we have to determine a north pole of the magnetic needle by using Ampere's swing rule. So what is Ampere's swing rule? According to this rule, if current flowing from this direction to this direction, that means feet to head. This is left, this is head of a human body, and this is left hand, this is right hand. Clear? If current flowing from feet to head, that means this direction, if current flowing from this direction feet to head, then the magnet, if we take a magnetic needle below this point, that means if there is a magnetic needle, then there is a man who is swimming over it. Clear? This is magnetic needle, and the face of the man towards the magnetic needle, and the current flowing through from its feet to head, then the magnetic needle which is below the man, then the magnetic needle deflects towards its left hand. That means if this is magnetic needle, this is the direction of magnetic needle, and The man is over the magnetic needle. Clear? And this is the direction of current from feet to head. Then magnetic needle deflect to its left hand. That means this is the direction of magnetic needle. And here, if there is a magnetic needle, then this is south, this is north direction, and if current flowing through this direction to this direction, that means feet to head, then magnetic needle deflect towards his left hand, this direction. Clear? And this rule is known as Ampere's swing rule. Clear? This is all about Ampere's swing rule. Next, we will go the important rule to determination of the magnetic field, the direction of magnetic field. The rule is known as right hand palm rule. You have learned, or you already learned your first year chapter, that is your vector or scalar vector chapter. You know what is right hand thumb rule. Now here also discussed what is right hand thumb rule, or this rule is also known as palm rule or grip rule. So according to this rule, this is the direction of flow of current. If we hold a conductor or current carrying conductor in right palm. Clear? If we hold this conductor, this is the current carrying conductor and current flowing through this direction. This is the direction of flow of current. If we hold this current carrying conductor in right palm, the direction, the thumb indicates the direction of flow of current. This is the direction of flow of current. If we call the finger, indicate the direction of magnetic field, because the magnetic lines of force, if there is a current carrying conductor, the magnetic lines of force develop around the conductor, which is perpendicular to the flow of current. So in this way, this is the thumb indicate direction of current. And if we call the finger right hand palm, if we call the finger of right hand, then call the finger indicate magnetic fields, the direction of magnetic field. That means this is thumb, clear? This thumb indicate the direction of current. We call a finger which indicate to the direction of magnetic field. So there is 2 points, this point A and then another point B. The point A indicates the, or you can write the direction of magnetic field at point A, which is inward, because the call indicate inward direction. So here the magnetic field which is inward direction, but at point B this inward direction, and then this point is outward direction. So in this case, the magnetic field, the representation of magnetic field, you know, that is B. The direction of B, which is perpendicular to this board, which is perpendicular to the board. This is plane, and the magnetic field which is perpendicular to the board and inward direction at point A. But at point B, the magnetic field which is coming out, this is the direction of magnetic field, this is the direction of magnetic field at point A, and this is the direction of magnetic field at point B. So this point, the direction of magnetic field which is perpendicular to this board, and outward direction. For point B, for point A, this is inward direction. For point B, this is outward direction. So the direction of magnetic field is important in this chapter, because throughout the chapter we will discuss only vector quantity. That means we will discuss cross product of two vectors. So you have to you have to know the direction of magnetic field. How can we find the direction of magnetic field? By using right hand thumb rule or right hand palm rule. Clear? Next, the representation of inward and outward vector. This cross represent inward direction. Inward direction of field, and the dot and circle represent outward direction of magnetic field. Clear? This represent inward direction, this inward direction, and this represent outward direction of the magnetic field. Clear? Suppose there is a current carrying wire. Example 1, there is a current carrying wire. This is the direction of flow of current I. Now you have to find the direction of magnetic field at point A and the direction of magnetic field at point P. So you have to find the direction of magnetic field at point A and direction of magnetic field at point P. So you have to use the right hand thumb rule. What is the right hand thumb rule? First the thumb indicate the direction of flow of current. This indicate the direction of flow of current, and this is the direction of the current. Now here we have to find direction of magnetic field, and here also we find direction of magnetic field. Clear? So this is the right hand thumb rule, and which indicate inward direction. So here the magnetic field which is inward direction, and this is the symbol of inward direction. So we can write cross and B vector, which represent the magnetic field due to this current carrying wire, which is inward direction and perpendicular to this board. Clear? But at point P, this is at point A, and at point P, this is the direction of magnetic field, and here the magnetic lines of force coming outward. So in this case we can represent the direction dot product, because this dot indicate outward direction of the magnetic field. So this indicate this is the representation of magnetic field at point P, which is outward direction. Next example, find the direction of magnetic field in example 2. Suppose this is the direction of current, and there is a point A, or there is a point P and another point Q. You have to find the direction of magnetic field at point P and direction of magnetic field at point Q. So how can we find the direction of magnetic field? First we have to use the right hand palm rule, and point Q is the direction of current, and the direction of current indicated by thumb rule. The thumb rule which indicate the direction of flow of current, and the finger indicate, the curl finger indicate the direction of magnetic field. Clear? So here the direction of magnetic field which is inward direction, and it can be represented by this cross, that is B vector. Clear? So at point Q is the direction of magnetic field which is perpendicular to this board. But at point P, what is the direction of magnetic field? This is the direction of current, and it's the direction of magnetic field. Clear? So at point P, the magnetic field, that is B. That means here the direction of magnetic field which is outward and perpendicular to this board. Clear? Next example, another one example. Suppose example 3, this is the direction of current. What does it mean? That means which indicate that the direction of current which is inward direction and perpendicular to this board. Clear? This is the symbol of inward direction. So we have to find here, or we have to find direction of magnetic field at point A. So how can we find direction of magnetic field at point A? So in this case, this is the direction of current. This is the direction of flow of current. Clear? The direction of flow of current. We have to find magnetic field here. So we have to use right hand thumb rule. This is the direction and this point. The direction at this point, which is inward direction. Here, the direction of magnetic field is this direction. Clear? It's the direction of magnetic field if current flowing through perpendicular to the board or inward direction. Clear? Another one example. Example 4. Suppose this is the direction or this is the flow of current. Now we have to find here. We have to find direction of magnetic field at point P. How can we find direction of magnetic field at point P? This point, that means it's the direction of flow of current in this direction, which is coming outer direction of the current. This is the direction of current. Now we have to find magnetic field at point P. How can we find? But in this case, we have to use right hand thumb rule. This is the direction of current and which indicate by thumb. Clear? So in this case, at point P, the direction of magnetic field which is inward direction, and this is the direction of magnetic field in this case. Clear? This is all about how to find direction of magnetic field by using right hand palm rule, and this rule is important to determination of magnetic field throughout the chapter. Clear? You have to remember this concept and remember this example. Clear? Which will help the determination of magnetic field in many cases. Clear? Suppose we know there is a vector. This vector is a vector and another vector b vector, and angle between two vector theta. So a cross b equal to c vector, because we know the vector product of two vector, the cross product of two vector which give a vector quantity. That means vector quantity means it possesses both magnitude and it possesses direction. So direction is important. Clear? So how can we find the direction of C? By using right hand thumb rule. Clear? That means first look at the vector A and then vector B. Then this is plane containing A vector and B vector. First you have to find the plane containing A vector and B vector, and this is the plane containing A vector and B vector. So first you have to place your hand, first A vector, then we have to come B vector, then B vector. Clear? This is A vector and this is B vector, and the thumb indicate the direction of C vector. Clear? And this is the direction of C vector. Clear? This is A vector and this is B vector, and this is the direction of C vector. So you can write here this point is C vector. That means the C vector which is coming outward direction. Another one example. Suppose there is a vector A and another vector, this vector B vector, and the angle between them theta. So B cross A vector equal to another one type of vector C vector. Now you have to find the direction of C vector. How can we find? First we have to know, or you have to imagine the plane which containing A vector and B vector. This is the plane A vector and B vector. First we will go B to A. Then first this is B vector, and we have to come towards A. Then call the finger towards A. This is not the process, because first we have to come B. First we have to come B, then towards A, or B to A. First place the palm on vector B and call your finger towards A. Then the thumb indicates the direction of C vector. So in this case, this is the direction of C. That means the direction of C is perpendicular to plane containing A vector and B vector. This is A vector and this is B vector. Then C vector which is perpendicular to this plane. That means inward direction. And this C vector which is always perpendicular to A vector, and this C vector which is always perpendicular to B vector. Why? Suppose this is the direction of B and this is direction of A. Clear? Or this is direction of A vector and this is direction of B vector. Then using right hand thumb rule, this is B and this is A. Then the thumb indicates the direction of magnetic field. This direction. Clear? This direction or inward direction. So this vector which always perpendicular to this vector and this vector which always perpendicular to this vector. So vector C which is always perpendicular to A and vector C which is always perpendicular to B. That means the vector C which is always perpendicular to A vector and B vector. This is all about to find the direction of magnetic field or the direction of cross product of two vector. Clear?